In this video, we'll continue our discussion of a line integral going through a conservative vector field by finding work. We're going to find work. So here's our vector field. Let's label it M, N, and P. And let's check for conservativeness, which means I check all derivatives of each part with themselves. Yes, let's do it. Okay. M, and let's do N first. So we switch our variables. This will be a Y then. And then this will be an X. And then we'll have M, and I'm going to do Z, so that means I'll do P here. And then we have to do N and P, and we just switch our variables. Z goes over here, Y goes over there. All right, so we're going to check this. M with Y is negative sine Y. N with X is negative sine Y, so we're good there. Okay, M with respect to Z, it's a 0. P with respect to X is a 0, so we're good there. N with respect to Z gets me a 2Z. P with respect to Y, the Y just goes away to get a 2Z. Therefore, F is conservative. So we can use the method in this section. All right. Now, if it wasn't conservative, we haven't said this much, but if it's not conservative, then we'd want to use the method. We would need to know a path, right? It wouldn't be path independent anymore. We would need to know what path it travels, since conservativeness is what gets us the path independence. All right, so we're going to work through this method again. Sorry, I think last time I'm doing it in our video series. So we'll work backwards. The gradient of phi is equal to f. F now can be redefined in terms of phi as its gradient. So phi derivative with respect to x, derivative with respect to y, and partial derivative with respect to z. And that's going to be equal to m in p. Then phi of xyz, right, is going to be equal to the integral of phi with respect to x derivative, partial derivative with respect to x. I'm going to start signing those correctly, dx. And then we have the integral of m dx, because that's what m is by definition. We just wrote that out in the line above. So I'm going to replace now with m, which is a nice pretty cosine of y, dx, which is even better, because that means I just get to introduce an x. But we do have a function that could have existed in phi that was only in terms of y and z, and maybe constants that disappeared once we took our derivative to get the terms of x. All right, so we have that now. I like to rewrite my function at this point. So the phi of xyz. Oof, my handwriting. Okay, xyz. Let's try it one more time. There we go. xyz is equal to x cosine y plus h of yz. The reason I like to rewrite it is then I take my derivative. So remember, we integrate, then we're going to take to the derivative to get the next part. So it's going to be phi with respect to y now. So that's going to give me a negative x sine y plus dh partial with respect to y. And we know that is going to be the same thing as n. We replace now with n. N was z squared. Yes, z squared minus x sine y. You see the x sine y's go away. So we have the partial with respect to y of z squared. I'm taking my integral to get to h yz with respect to y, because the partial is with respect to y. So I'm just going to get a y z squared plus g of z. If you need to set up that integral, please do. So I like to rewrite my function now. So phi of x, y, z, this is our potential function. We get x cosine y, and then we have a new part to add in z, or sorry, yz squared plus g of z. And then again, remember, we integrate, and then we have the function, and then we take a partial to get the second part of our gradient, or a vector field, which is going to be the same thing since it's conservative. Then we get a function, and then now we're going to integrate. So the integral of phi with respect to z now, the last part, and I take the integral of what I have, I'm going to get 2yz plus g prime of z, and then we're going to set this equal to p. All right, setting equal to p. What was p? I have it on my notes. 2yz. This tells me, after all notes, we can see that g of z is going to be c, constant. All right, let me shrink this up to make a little bit of room to finish up my problem. All right, so now I have the function. So phi of x, y, z is equal to x cosine y plus y z squared plus c. And then we have the fundamental theorem since it's conservative. So thus, our line integral of vector field f dotted with dr, which is work, is equal to phi of, and we just plug the points in. Okay, the points, I'm not going to scroll up. I got my notes here. I got 2 pi 1 minus phi of 0, 0, 1. If you plug all that in, what you're going to get is 2 plus 2 pi.